So now let's start talking about multiple regression. So remember in linear regression, we had a single predictor or explanatory variable, and the linear regression model was y equals mx plus b. Remember, m was your slope, x was your x value or your independent value. So let's remember something there. And I'm going to pop this up. So x can be called the predictor, explanatory variable, or independent variable. Oops. So if you hear those, it's just talking about the same thing. Okay. And I'm just going to make sure that we have that on there so you understand it. So remember that x can be either the predictor, explanatory, independent variable. It's the same exact thing. Okay. So this formula y equals mx plus b, where m is the slope, x is the x value, and b is the y-intercept, can also be written as this. Y equals beta 0 plus beta 1 x1 plus ei. So this beta 0 is the y-intercept. It represents the same thing that this lowercase b up there is. Okay? b1 x1 is the slope and the x value, and the ei is the residual or the error term in the regression equation. So in multiple regression, we have more than one predictor. So think about that. That's your x value. You can have more than one x value. And remember, x values can be called explanatory, predictors, or independents. So the multiple regression model is defined by the relationship between a dependent variable and a set of independent variables. So suppose we have two predictors, and I'm going to call them x1 and x2, and they can either be continuous or categorical. Remember, continuous data is data that can have decimals in it. Categorical is data in categories. So here's what your equation is going to look like. Y equals beta 0 plus beta 1 x1 plus beta 2 x2, and e with the little I. So again, beta 0 is your y-intercept. The ei is the residual, the error term. But now your beta 1 is the coefficient of x1, which means it represents the effect of x1 for individuals with the same value of x2. And beta 2 is the coefficient of x2, which means it represents the effect of x2 for individuals with the same values of x1. So basically what we're talking about is we are looking at the relationship between the x's. That's all that really means, is because now I've got more than one x, and I've got to make sure to measure how those x variables are, their relationship to one another. So we call that beta 1 x1 and beta 2 x2 partial regression coefficients. Each multiple regression coefficient represents the relationship between the predictor variable and the dependent variable, conditioning on all the effects of the other predictor variables in the model. Okay, that's really important. Let me say it again. So these coefficients, these partial regression coefficients is looking at the relationship of that actual predictive variable in terms of the dependent variable and the relationship it has with the other predictive variables. So there's a lot going on when we do multiple regression. So you have assumptions for multiple regression. You have one dependent variable that's measured at a continuous level. Yes, there are different types of regression that do different kinds of dependent variables. For this class, we're only going to look at ones that are measured on the continuous level. You can have two or more independent variables that are either measured at the continuous or the nominal level. There should be independence of errors, which are residuals, and we'll go into this. There should be no multicollinearity. There should be no significant outliers, high leverage points, or high influence points. And the errors, we also call these residuals, should be approximately normally distributed. Okay, we do hypothesis tests for multiple regression. It's the same as what we did for linear regression. The null is the Pearson correlation coefficient equals 0, which means there's no difference. And the alternative is the Pearson correlation coefficient does not equal 0, which means there is a difference.